All right, so this week we're going to be talking about variables, expressions, operators, the things we need to actually do some work with our programs. Almost every program you write is going to be you somehow manipulating or processing data. And most of that data, you're not going to know what it is at the time that you're writing your program. Your programs are going to be sort of generic to work for any particular value you might get. Take a really simple example. You're trying to write a tip calculator. Well, how are you going to write a tip calculator if you don't know what the person's meal cost was, right? Like if you don't know what the cost of the tab is, you won't be able to calculate the tip. You have to have something to sort of generically hold that value so that you can then, do some work on it. Maybe that's coming from a user, maybe it's coming from a sensor, maybe it's coming from a server somewhere. But regardless, you're not going to know what that data is at the time that you're writing your program. You're creating sort of a generic solution that will work for any particular inputs. And so we need to have a way that we can hold those inputs. We would often call these variables. They're variables because they can vary in, value. They can be one value at one point, another value another point. They can change, but they're a way of holding on to a number, a character, a string of characters, a piece of data, something, right? Some sort of larger, more abstract class that you might create later on. So, at a high level, you can kind of think of variables as a box. They're a way that you can sort of take a value and put it in the box, and so then you know you've got that value in the box. In the box, you give it a name. That name is important because you can use that name to then refer to the value inside the box when you're creating expressions. So, for instance, for a tip calculator, you might want to say, well, I want to multiply the price of the meal or the cost of the meal, the amount of the tab, whatever you want to call your variable, and I want to multiply that by 0.15, right, to get a 15% tip. I can just say, well, I want to take cost times 0.15. Cost will evaluate to whatever is inside the box at that time. And so that sort of allows you to generically write expressions that can perform operations on numbers you don't know yet or you're getting from somewhere else. You can also create variables to create intermediary values as you're calculating something larger. C++ is a typed language, a strictly typed language, and so that means that you have to, at the time that you create the variable, the time you create the box, you have to say what type of data that box is going to hold. There's going to be a lot of different type options, but once you create a variable that holds a particular type, you can't change that. It can't suddenly, at one point hold integers and at another point hold a string. C++ won't allow that. Languages like Python and JavaScript will. Those are not strictly typed languages. And so, in a way, you get a little bit more safety and performance out of C++, but at the cost that it's probably a little bit more annoying to learn in the beginning. But you have to specify a type. Once you do that, you can assign a value, and we'll talk about what those types are here in a second. At that point that you've got the box, you can now assign a value to that box. Once you assign a value to the box, you can use the name of the box to refer to the value that's inside of it. So, this is a less high-level way of thinking about it. When you create a variable, what you're really doing is assigning a memory location to a name. Now, you're not actually specifying a specific memory location. It's actually a memory offset based on the pages that your program is assigned at runtime, but let's ignore a lot of the little details. You just have to know that somewhere in memory, somewhere in RAM, there's going to be a memory location that name is now associated with. And anytime you use that name, you're going to refer to that memory location. The type will not only determine how you're going to interpret that data in that location, but also how much memory you need, because not all variables are the same size. Some are larger, some are smaller, depending on the type of the variable. To declare a variable, you just have to give the type and a name, in this case a semicolon. Now I know we haven't covered the float type yet, but we'll talk about that in a second. But that's going to be the sort of standard way to declare a variable. Declaring a variable is the same thing as sort of creating a box. It's making that assignment. This memory location I want to refer to with this name. Because it's a float, you'll know that it's supposed to be this many bytes big. But you don't have to worry about any of that. You are not programming in assembly language. You're programming in C++. So you can still think of it as just a location where you're holding a value. By the way, you'll notice a couple tips here. One, when you choose variable names, choose descriptive names. That is probably the best form of commenting you can do in your code. When you have a variable name that's meaningful and not confusing, right, then people will understand your code. Your code will be 100 times more readable than if you call your variable name X, which is terrible, or, and by the way, there are some exceptions. If you're talking about Cartesian coordinates, where X is clearly defined mathematically, like it would be weird to call it anything other than X, then call it X. But if it's supposed to represent, somebody's name, don't call it X. That's not helpful. It works, but it's not creating readable code. Something that can very easily be, fixed later if something needs to be changed. The worst thing you can do is call something by something that is deceiving, right? Sometimes students will put in code and it's like, oh yeah, I've got, let's say the cost of the meal times, the tip rate or something. But instead of saying the cost of the meal, they're like, tip amount times tip rate. Tip amount? No, that's the thing I'm trying to calculate. Like you're calling the cost of the meal something that is something else that I would expect in the code. So now I'm going to be really confused. And if we're doing something as simple as a tip calculator, imagine what, if you're doing a really large project amongst a team of people with millions of lines of code, right? Like descriptive names are the best. Sorry, I went off on that a little bit too much. Also, by convention, we write all of our variable names in camel case. Now, by the way, this is not true for every single company. Some companies will use other things, but for the most part in C++, it's traditional to have variable names in camel case. Camel case just means the first letter of the variable is lowercase, and then for every new word in the name of the variable, you make the new word uppercase, so that you can see where the breaks are in the word, if that's helpful. To store a value into your variable, you use the assignment operator, which looks an awful lot like an equal sign and will cause problems later, but for right now, that is the assignment operator. It sets a variable to a particular value. In this case, interest rate will have the value of 4.65. Now, by the way, you can combine these things together. You can actually initialize a variable at the time you create it. So here I have one line where I create a variable, I declare a variable, and I assign it a value all in one step. This is actually really nice in C++ because unlike other languages where if I create a float interest rate, semicolon, I don't assign it a value, some languages will be kind enough to say, oh, well then I should reset that memory location so that it has the value of 0. C++ doesn't do that. C++ says, oh, I'm just assigning that memory location with this name, right? I'm giving you a box, but by the way, there may have been something in that space before, and so whatever was there before is still in your box, right? Whatever was in that memory location is still there. You didn't tell me to get rid of it, so I'm not going to. That can be really annoying. So it's nice to initialize stuff, even if you just initialize it to 0. At least then you'll know you'll have a sort of specified like default, and you're not going to get really wonky answers, which can happen sometimes. So if you actually want to print out the variable like we did last week, no problem. All you have to do is just send it to cout, just like you sent those strings last week. So cout, arrow, arrow, here we have a string, your interest rate is, and then we have another arrow, arrow, because we're sending something different. You have to have only one thing in those arrows. If it's an expression and it evaluates to one thing, that's okay too, but we'll get to that in a second. So at this point, all I'm doing is I'm sending interest rate, but you notice there's no quotes around interest rate. Interest rate is actually going to be evaluated. So interest rate will have whatever the value is inside the box. If I had put quotes around interest rate, I would just be sending the string of characters interest rate, which would say your interest rate is interest rate, all shoved together, percent. That's not what I want. I want that 4.65 number. So your interest rate is interest rate, not in quotes, and then that will actually evaluate, we'll find the answer to 4.65, and then we can go on. Now, by the way, I could also multiply the interest rate by something right there. That's fine because I would take the interest rate, it would evaluate to that number in the variable, and then I could say multiply it by 2. Okay, well then I'm doubling your interest rate. That becomes one number, and that one number gets sent to the cout. So you can expand with expressions and operators, which we'll talk about in a second. There's also something called constants. Constants are very similar to variables, although they're stored in a different location, which actually is a good thing. It makes them slightly more efficient that way for reasons I won't explain right now, but it has to do with the fact that you don't have to have multiple constants if you have the same value. Anyway, but they're also unchangeable, right? You can't change a constant once you set it, which means you have to initialize constants because once you create it, you can't change it. So you have to initialize it to something. And yeah, in general, they're helpful for like values where maybe you're going to use it in a lot of locations. And so you'd rather create a constant and then use that constant in all those locations. So if you ever did have to change it later, you could just change it in one place and it would change it in multiple. There are a few other reasons why we'd want to use constants. Like for instance, if you're doing keys for key value pairs in dictionaries, and you want to get a compile time error as opposed to a runtime error if you accidentally misspell something. But that's not going to make any sense at this point. There's reasons for them. The first one is probably a good low-level explanation for why you might want a constant. But they work just like variables, other than the fact that once you create it, you can never change it. You can change it in code, obviously, but you can't change it programmatically while it's running. By the way, the convention for naming constants is completely different because they're kind of wonky. And so we do them all uppercase with underscores for spaces in between the words. That makes them stand out in the code, so you know when you're using sort of something that's going to get replaced by something else later on. So we said C++ was a static typed language. That means that it's strictly typed. Everything has to have a type, and once you have that type, it can never change. So, yeah, what are the different types we can create? These are all of the different types you can use to store whole numbers, shorts, ints, and longs. They only vary in the number of bytes that you use for those variables. The number of bytes matters because the more bytes you use, the larger a number you can represent. And so even on 64-bit processors, we still sort of use 4-byte integers. And with that, you can represent numbers approximately 2.5 to negative 2.5 million to positive 2.5 million, billion, which is a good number. We're about to pull it up here in a second. It's either billion or I'm now doubting myself. How many years have I been teaching this? I'm pretty sure it's billion. But point being, yeah, it's definitely billion. 2.5 billion to negative 2.5 billion. You've got a range, right? That's generally good enough for most things, right? But if you're doing anything scientific, if you're doing anything sometimes financial, you may need to use a long because you just need more memory to represent larger numbers. But that's the only difference. Amongst these three, by far the most common is int. So that's the one you'll probably use the most. When you're creating literals for integers, meaning like I want to assign it to a value, so I'm going to assign it to a literal, right? Or I just want to use a literal somewhere that will be interpreted as an integer. You can write it as a number, 42, that's fine. 4200 is fine, you can go larger. You cannot put commas though when you go to these larger numbers. The computer just won't recognize the comma. Some modern languages do, not C++. So only numbers, no weird characters in the middle. If you were to put 4200.00, you and I both recognize that that's kind of an integer because there's nothing after the decimal point and it's equivalent. But C++ will not. It will treat that as though it's a double type, which we'll get to in a second. Because you can only represent so many numbers with those memory locations. Picture if you had only 4 digits you could work with, and you had 9999, so 9,999, and I added 1 to it. What would happen? I'd go from that to 0, right? Because there should be a 1 that appears over here with my 4 zeros, but I can't represent the 1, so I just go from the largest possible number to the smallest possible number. Trust me, in binary, the way this works is it essentially kind of works like an odometer. You go from the largest number you can represent to the smallest number you can represent, which means this number, which happens to be, I was correct, not 2.5 billion, I guess it's like 2.15 billion-ish. But to get to that number, right, you have to, once you get to that number, if you were to add 1 to it, it's like an odometer. It rolls over and suddenly you're not at all zeros. You're just at the lowest possible number you can represent, which in this case is negative 2.1 something billion, right? So you took a really large number, you added 1 to it, and you got a really negative number. C++, it's an overflow error. You should watch out for these. There's not a whole lot of safeguards for them unless you're in a system where you're using a class for numbers. That can kind of help you out, but just know if you need larger numbers, then start using longs. And by the way, there are actual types longer than longs in various libraries, so you can have long longs and long longs and stuff like that to use more bytes to represent those numbers. There's also a problem with narrowing. So C++ will allow you to do whatever it is you want to do because it assumes you know what you're doing, which is a terrible assumption to make, but it does. So if I have an integer, and then I take that value and I assign it to a short, the value of b in this case is going to be -1. Why? Because when you slice off the bits, that just happens to be what the binary is for -1. In other words, I took something that had more bytes, right, and I stuck it into something that had less bytes. As an example, and narrowing is always the problem, not the other way around. If I have a carton of 12 eggs and an empty carton that can hold 18 eggs, and I were to do this, right, flip it over, I would have 12 eggs inside my carton that holds 18. That's perfectly fine. If I have a carton that holds 12 eggs and I take one of those little cartons that only holds 6 and I put it on top and then flip everything over, I'm going to have a carton that has 6 eggs and 6 eggs on the floor. I just lost 6 eggs. Right? More importantly, it's not the losing of, it is the losing of the bits, but I've got something that I did not expect, right? I've got something worse than an error. Because, I say narrowing errors. They are errors, but they're not going to show up as errors in the computer. The computer's not going to say, oh, hey, there's an error. C++ just is going to give you the wrong number. And that's even worse. Suddenly you owe somebody a lot of money that you really shouldn't or something, right? It's potentially a problem. So if you do want to hold numbers that have decimal types, right, then something with a decimal point and some stuff after it, there are 2 types to do that, float and double. By far, the more popular of those 2 in practice is double. And that has to do with rounding errors. You're less likely to get a rounding error with a double, so we use doubles more often. And that's because binary is sort of an imprecise way to hold decimal numbers. And you may every once in a while run into something where it's like, hey, why is this like 1.99999999999 instead of 2? There's a reason for it. It's just kind of the way binary works. A lot of times systems will try to correct for that. Sometimes they don't. But regardless, you're less likely to get rounding errors with doubles. And so that's the one that we use more often. But anytime you have a number that has a decimal point in it, it's a completely different type than something that only holds integers. Your computer, for the most part, uses integers for everything, right? The number of pixels on your screen is an integer. You can't have half of a pixel. There's a lot of things. That's the whole reason computer scientists study discrete mathematics, right? Because I don't need to worry about the space in between 1 and 2. It's either going to be 1 or 2. But for a lot of scientific reasons, we need to have these floating point numbers. And so they exist. But they run down, if you remember from the discussion of the CPUs, they run down completely different pathways in the ALU. If you want to add 2 integers together, that goes through one pathway, one circuit, to get the answer. but doubles will go through a completely different one. And so floating point types versus integer types, you need to keep them sort of separate. You can convert back and forth, but notice that if you take a double and you put it into an integer, you're going to be losing everything after the decimal point. Floating point literals, perfectly fine. Basically anything that has a dot something on it. If you want a literal to be treated as a floating point, you can put the .0 there specifically. Although remember, if you take an integer and you put it into a floating point, well, that's okay. You can hold more information than the integer can. And so that implicit conversion happens pretty quickly in C++. But if you take a floating point and you put it into an integer, you lose everything after the decimal point. You can also represent numbers in scientific notation. That would be anything that's, a mantissa and an exponent. So, 1.2 times 10 to the negative 6, right? Something like that. The 1.2 is the mantissa. You don't really need to know that part, other than that's the part that goes before the e in that syntax. And then e represents times 10 to the power of, and then after the e, you write the exponent. And that will give you a nice scientific notation. There are also, for all of those integer and floating point types, unsigned versions of those. What that means is that if I have like an unsigned integer, I'm still going to use 4 bytes to represent that integer, but I'm not going to use one of those bits on the very first byte to represent whether or not it's positive or negative. And because of that, that means that I can use that 1 bit, which is like the highest bit, to be able to represent numbers rather than whether or not it's positive or negative. If you think about that, what that does to our thing, if I had 4 bits that I use to represent numbers and a 5th one for the sign, right, then 9999 would be the highest I could go to, right, about 10,000. But that's because I have to have this one to represent negative 10,000 or negative 9999, right? If I were to use this one to represent numbers, then all of a sudden I can go from 10,000 to 99,999, right? I go up by 10 because I'm using base 10. But with unsigned binary numbers, we can only go up by 2. What that means is essentially instead of going from negative 2.1 something billion to positive 2.1 something billion, I can now go from 0 to 4.2 something billion, right? Like I have the same number of space to represent numbers, I've just shifted everything so that now I can no longer have negative numbers, but I can go twice as big on the positive side. If that makes any sense, before I hit my rollover, edge limit. So unsigned ints are kind of popular. There's a lot of cases where you don't need something to be negative. If I have something like your student ID, right? Your student ID, no student will ever be issued a negative student ID. That's never going to happen. So I might as well use an unsigned int so that I can have twice the number of student IDs, right? It's the idea of unsigned. Now, for some non-numeric stuff. A char will hold a single character, right? Like an exclamation point, uppercase B, the ampersand, which is a great ice cream place in town, just saying. Like it holds a character. In most cases, because it's a C++, an ASCII character. And so, yeah, it's just a type that holds a single character. And we represent it as a character, even though it's actually just a number on the ASCII chart. But we know how to interpret it. So we can have character A equals uppercase B, character B equals the space, because remember, even though you can't see it, space is a character, or the hashtag, whatever, pound sign, hashtag. I say hashtag. I feel like I'm old enough. I should be able to say pound sign, but whatever. The idea here is that these character literals are written in single quotes, not double quotes. Double quotes are for strings, single quotes are for characters. There's also some weirdness with characters because they are just like numbers, but we interpret them as though they're from the ASCII table. That means that I could do something like this, where I say character A equals 66. Now, by the way, some IDEs won't let you do this. They'll kind of cut it off because they're trying to help you out. But that's not necessarily part of the language, and it should work. But I've noticed a few IDEs will actually prevent that from happening. Anyway, if I were to print that out, what comes out is a capital B. Why? Because capital B is number 66 on the ASCII chart. So what is, capital B plus 1, the character capital B plus 1? It's the character capital C. If the compiler interprets it in that way, then, you can kind of bounce back and forth between the numbers and the characters. But, don't. Why would you do that? It's purposely being confusing. So if you think about these different literals, right? 5 is an integer. I can do math on that. 5 in single quotes is a character. I cannot do math on that. That is just something that gets interpreted. 5.0 is a double. I can do math on that. 5.0 in double quotes, or quote marks, right? That's a string of characters. I can't do math on that either, right? I'd have to have some way of converting one to the other, which there are, but we'll talk about that later. Then what about strings? Strictly speaking, strings are not a native type. They're an array of characters, which is a type of structure, which, yada. But you can think of them as a type. In fact, if you use the class called string, which I'm going to encourage you to do so that we can use C++ type strings as opposed to C-style strings, then you get a whole lot from strings. But they're a class. You're technically creating an object, but it's set up to work like it was a native type. So let's just treat it like a native type. If you're going to be using strings, I would encourage you to include the string library at the top of the code. That's going to give you a few more options when it comes to stuff. And we'll talk about those as we talk about sort of manipulating strings later on. But at this point, we might as well just start using C++ strings straight away. There will be some things that we use the old C-style versions of, like arrays, for instance. And that's just because of conversations with people from engineering and stuff like that, where there are practical purposes for using those old C-style, native arrays. But for right now, for strings, we can just use the string library. And hopefully that'll change for other stuff too. So here I can create a variable of type string, and I'm going to be perfectly okay with you saying that. You don't have to say I'm creating a string object, but you technically are, right? But string name equals Zaphod Beeblebrox, and then I can cout and then send that string to cout, just like I send those string literals, right? I have a string literal, ahoy there, comma, space. I'm sending that string literal to cout. Then I can send name. That variable has a type string. Cout knows what to do with strings, so perfect, it sends the name. Then I can send an exclamation point, good to meet you, whatever else. I can just keep sending stuff to that string, to that cout. The last of the types that we will actually care about today is a bool. So what's a bool? A bool is a value that can only have one of two possible values, true or false. It comes from Boolean logic, going back to that whole discrete mathematics stuff, and predicate logic. But the idea here is that there are some things that have numeric answers, and there's some things in this world that have logical answers. So for instance, 2 plus 3 has a numeric answer. The answer is 5. 2 less than 3 has a logical answer, right? It has the answer true. 2 is less than 3. And so in this case, the bool would have the value of 2. So some expressions will return numbers and some expressions will return Booleans. And can you mix the two? Yes. Should you? Probably not. But there's going to be, no, you will. There's going to be exceptions to every rule. Maybe I want the Boolean value, but I have to take this variable and multiply it by 2 before I compare it to this other number. There we go. We've got a numeric something that's going to be combined with a Boolean expression. But bools also have their own weirdness, which is that in C++, the rule is if it is null or it is 0, it is false. Everything else is true. So the literals, true and false, obviously false is false, true is true. 0 is false, 1 is true, 42 is true, negative 42 is true, the character A is true, the object your mama is true, everything is true, except for null, which is nothing. We'll get to it when we talk objects. And null is also false. But for right now, you can just think of 0 is false, all other numbers or other values are true. By the way, is there an ASCII 0? I think there is an ASCII, there has to be an ASCII 0, right? If there is, it's an invisible character because it's part of those really low numbers. And so I wouldn't even know how to get that character for you. But regardless, if it has the value of 0, it's false. Otherwise, it's considered true. It's non-zero. Other types that we'll talk about later in the semester, pointers and structs. One is used to hold a memory address. The other is to use sort of your own type. So it becomes like you can create your own structs that are essentially combinations of other types put together to represent something. We'll talk about those later because they have their own weeks. By the way, C++11 added the ability to infer type using auto. So here, if you are initializing a variable, then you don't necessarily have to specify the type. You can use auto. You are specifying the type, though. You're doing it based on the literal on the right-hand side of the assignment operator. So here, auto A equals that really large number that's clearly larger than 4 bytes. That's going to be a long. A is going to be a long. It's being inferred by C++ in that line. So even though you didn't type it, you got it. Now there are some kind of really complicated cases, especially when you're dealing with like closures and stuff, which you don't even know what a closure is. But I'm just saying there are cases where like, you need auto, but for the most part, you don't really need it. So don't use it. It seems kind of lazy, but I mean, it's there. So if you want to, go ahead. Who am I to stop you? Anyway, auto B equals that B is going to be a character, and C is also going to be a long because we know what the value of A is, right? So it evaluates A. Assignment operators always evaluate the thing on the right first and then do the assignment. So it evaluates A, sees that A is a long. Since the thing on the right is a long, C becomes a long. Now, we've got variables and literals. Why don't we combine these things into larger expressions? And so here are some of the basic operators. I'm actually going to skip 2 of these today, but we'll talk about them later for a reason. But the idea here is that we can combine these numbers and variables to do some math, create expressions that actually have value, etc. So what is the value of the result variable here? Kind of doing this in the form of a test. Here I've got an int number equals 5. The number is always going to be 5. I'm just doing this so you can see that, oh, hey, look, I can combine variables and literals together to create expressions. So the result is going to be whatever that number is plus 2. Well, number is 5, plus 2 is 7. And the idea is here, don't overthink it. Integer math is like elementary school math. Like if you're thinking of the math you learned in the 6th grade, you're too advanced. Take a step back. It's easier than that. It's really easy. Number minus 2, well, 5 minus 2 is 3. Done. Number times 2, and in case you're not familiar with like Excel and stuff, the asterisk often represents multiplication. So 5 divided by 2, or sorry, 5 times 2 is 10. You've got this. I could say 5 divided by 2. We use that / to represent division. Now here's where it gets a little weird, but you just have to go back to like the 3rd grade, right? 5 divided by 2, you all know that that's 2.5. But remember like before you had decimal points, you'd have like that weird kind of swoopy and then a straight line thing, and you'd have like the 2 on the outside and the 5 on the inside underneath the line. And you have to go like, how many times does 2 go into 5? It goes into 5 2 times. 2 times 2 is 4. 5 minus 4 is 1. So it's 2 remainder 1. That division that you don't do anymore, that's what we're doing here with integers. So when I say number divided by 2, the answer is 2. You don't get decimals. You get the old, whatever they called it, long division. You get that version of division. So you just get the quotient of that multiplication. 2 goes into 5 2 times. And if you want to not even call it divide, if you want to call it the goes into operator, because it'll help you remember, do it. It's 3rd grade math, not 6th grade, right? Now, how do you get the remainder, right? Because that's also important to know. You get the remainder using the modulo operator, which why they didn't call it the remainder operator, I don't know. I'm sure if I had taken more math, I would know why it's called the modulo operator and not the remainder operator, but whatever. Worst of all, they used a percent sign, which is actually another thing that has meaning in math. So I can't help you. I'm not Dennis Ritchie. I didn't design this stuff early on. Here's the thing. It just gives you, this is still 5 mod 2, is how we would say it. 5 mod 2. And in this case, I'm not going to get 2. That's the quotient. I'm going to get the remainder after division, which is 1. 5 divided by 2 is 2 with a remainder of 1. I get the remainder. All right, now that we've gotten through that weirdness, let's talk about floats. So here, number is still an integer, but my result is a float, and that's important because if my result wasn't a float, I would end up truncating whatever was on the right. Whatever's on the right might calculate as a double, right? But it wouldn't get, or a floating point number in this case, but it wouldn't get put in as a float. It would get sliced off at the decimal point, and I'd only get the integer because my box can't hold anything with a decimal point, right? So here, 5 divided by 2, but now I said 2.0. Wait, because I put 2.0, it's going to see that literal as a double literal. And whenever you have an integer and a double literal, it's going to assume that you want the double amount, which means I get my 2.5, just like we would have expected from the beginning. Here I've got a float 5 and a float result, and now I've got number plus 2 times 5. So what is the answer here? Well, just remember C++ uses the order of operations, which means I am not going to add 5 and 2. I'm going to multiply 2 by 5, which gives me 10, and then I'm going to add the 5, which gives me 15. You may have heard of the phrase, please excuse my dear Aunt Sally. First, you work through your parentheses, then your exponents, then your multiplication and division. Remember, multiplication and division happen at the same time, left to right. There's not all multiplication and then all division. And then Aunt Sally is addition and subtraction at the same time, all the way from left to right. Because multiplication and division are actually kind of the same thing, and addition and subtraction are kind of the same thing, but talk to your math instructor. Point being, this would evaluate to 15. And by the way, notice we're adding stuff. We're creating a larger expression. Now, what if I wanted to add the number and 2 before I multiplied by 5? Well, no problem. Just put in parentheses. Put in parentheses, now I do 5 plus 2, which is 7, times 5, which is 35. If you ever need to be explicit about what you want to do first, just use parentheses. It's the easiest way to go. Now, you can also get values from other functions. Later on, you'll create your own custom functions. You can use those functions to get other values, but for right now, we'll just talk about stuff that's in libraries. CMath has got a bunch of functions. Probably the 2 most common are the ones that we see most often are pow, which just takes something and raises it to another power. C++ doesn't have a exponent operator like Python does, where you do star star, or even Excel has that little caret thing. You can't do that in C++. So if you want to do exponents, you either have to do a loop and then actually multiply that many times, or you can call the pow function, send whatever variable you want, or literal, or an expression that will evaluate to something, and then comma, the second thing you send is the exponent you want it to raise to, and you can calculate that too. That could be an expression. To do this, you have to include the CMath library in your program at the top, just like you did IOStream. And it'll still be in angle brackets because it's one of the already built, pre-compiled binary libraries. All right, so That's how you would get a value. And by the way, notice that we're setting number here, but you could also use that POW inside of a larger expression. So I could take, POW number and 2, which would be 5 squared, and then divide that by something else, and then multiply it by the square root of something else, which, by the way, the SQRT stands for square root. So it'll take the square root of a number. Point being, you can use all of these, and some parentheses if you need them, to create larger and larger expressions. Now, the last thing we're going to talk about, just because it's going to be practical for your assignment this week, is getting responses from users. At this point, you can do some stuff if you're just, writing, whatever, programs. But one of the things you could do is actually get a response from the user. Figure out hey, how much was that meal? And I can tell you how much tip you owe. Stuff like that. So to do that, all you have to do is use a different object rather than cout. So cout stands for console out. It means I am writing to the console. I'm going out to the console. The standard output, the console out, for most computers is the screen. The standard in for most computers is the keyboard. And so cin is console in. This is going to get information from the user at the keyboard and put it into something, hopefully a variable, that you can hold on to that value. So here I create a variable called int user response. I initialize it to 0 because I'm a good boy. And then I use the cin object, and now notice those arrows are going the other way. You send stuff to the cout to get it to the screen. You bring stuff from the keyboard to put it into a variable. And that can hopefully help you remember which way the arrows go. But this is a stream that's going to come from the keyboard, put it into a variable, and so now user response will hold something from the user. Hopefully, they gave us an integer. If they didn't, your program will crash. For right now, because cin is a little bit finicky, and later on we'll talk about how you can kind of do it a little bit better with more of a get line, and then, convert it, and you can kind of handle issues that might pop up. But for right now, just assume that everybody's going to be a good player. So if you ask for an integer, they'll give you an integer, and cin is going to work just fine. By the way, I will say this, cin will only grab up to the first white space character. So if you're asking for a name, which I'm about to do here in a second, you cannot put in two separate words. Or if you do, you actually have to put cin, comma, comma, first response, or comma, comma, arrow, arrow, first response, arrow, arrow, second response. And then it'll grab the first thing they typed in, put it into the first variable, take the second thing they typed in and put it into the second variable, because that space in the middle will separate the two. But for right now, one thing at a time will be enough. So here, I'm just giving you the tip that if you are going to use the cin command, the way cin works is it stops execution. And you just sit there with this little cursor blinking, and hopefully your user knows what they need to type, right? Otherwise, it just looks like your program crashed. So if you're going to use cin to get something from the user, I would highly recommend you use cout to tell them what it is you want. That way they'll know what to type, and they'll also know that, oh, you're waiting for me to type something. You asked a question. I can now answer it. They'll give you some response. Here, I'm doing the exact same thing with strings. I believe you have to have the string library in order for cin to work with strings, but I'm not entirely sure about that. So, but I suggest you do it anyway. So here I create a string called name. I say cout, what's your name? And then cin name. That's going to cause execution to halt. Blinky cursor. But I've got my little prompt there, so it's like, oh, what's your name? Oh, my name is Brian. I type in Brian, I hit enter. That takes those string of characters, sends it over to name, right? And then at that point, name has the value Brian. So then cout, hello, Brian, exclamation point. It's a really simple program. You can try it out yourself. But your assignment will obviously have you do some input, some output, and some sort of processing of data. And that is pretty much it for this week. Hopefully you'll be able to write some expressions that have some meaning and actually do something that has value. Anyway, have a good week.